So today's topic is viscosity. That's what we are going to cover. So this happens, okay, just like say if I take in viscosity, basically we talk about flow of liquids, okay, flow of liquid, or even actually gases also we can apply this, okay, whatever we are going to talk about. We are talking about flow of liquid or gases, and this happens, okay, and this happens. See, if I have a liquid which is flowing in a pipe, let's say this is a pipe, or actually anything, even in a river you can just compare it, okay. So what happens is this, okay, let me just make this diagram, okay. Again, let me not cover the upper half, the upper part is not covered, okay guys. See, so I do not know, did I make sense my diagram? Okay, so you have no, very bad diagram, okay, very bad diagram. Okay, let me draw again properly. See, you have this, okay, you have a liquid. I told you can also compare it with the gases. You have a liquid which flows in this direction, the way the direction where I'm drawing these lines, no, the liquid flows in that direction, okay. I'm going to show an arrow also, but this is the liquid I have right now. And if I ask you, okay, if I imagine this liquid to be moving, okay, what do you think, guys? All the liquids, they move with same speed or different speed? Obviously your answer is the liquids will move with different speeds. Example I can give you, if I want to make a liquid move like water, okay, water, you want the liquid that is water to move, it's quite alright, okay, very easy for water to move, okay. Obviously you have noticed this, okay, you can transfer water through pipes and all, that's very easy, okay. You want to do the same thing, but let's change the liquid, okay. This time let's take honey, no, honey, okay. Now think and tell me, okay, is the flow of water and honey same or different? Yes, you have to be interactive, guys. Don't be lazy, okay. It's winter, I know, but don't be lazy. Different. The flow is going to be different, okay. So the flow of liquid like your water will not be same, okay, like the flow of another liquid which is like honey, right? Okay, what is the difference? Can you tell me what is the difference in their flow? What is the difference?
So water flows more easily than honey.
More easily, okay, not so easily. Flow is not so easy, okay. What does it mean? Easily and not so easily, what does it mean? Anybody who can just give some different way of what she wants to say, different way of looking at it? Speed, okay, water has more speed, agreed.
So honey is dense.
Honey is dense, okay, dense is correct. Honey is more dense, water has more speed. What else do you think we can talk about?
So water is smooth.
Water is smooth, okay, smooth. Anything else? Water is smooth. Honey is not smooth, okay, fine. Honey is sticky. Yes, very good. Honey is sticky. Sticky, yes, correct. What else?
So the forces of cohesion in between the water molecules is less than that between the honey molecules.
Okay, correct. The force of cohesion, you can see that, is small, right? Is small, okay. The force of cohesion in honey is large. Cohesive force is large, or very strong, let's say, very strong, correct, okay. I'll agree with that, okay. What else? We are just talking, okay. Jyoshna just joined, so we're just talking about the difference between honey and water, okay. Yes,
so honey is thick, water is not thick.
Honey is thick. Thick is not the word, okay. You should have used dense, okay. No,
Yes,
okay. Thick also sometimes we may use, but actual word is what? Dense, okay. That is actually that should be the word, okay. So you should use dense, okay. So you're okay, right, with that. You can use thick also actually, but much more better one is dense, okay. Yes, yes. Anything else? Anything else? Okay. Now let me tell you. Done. Okay. Prayash also has joined very late. Okay. Now see. So yeah, you are right. Okay. Water, the way water flows, okay, and the way what the honey flows is quite different. Honey is thick. Honey is dense. Honey is sticky. The cohesive force, okay, the molecules with which, right, the honey molecules pull another honey molecule. Okay. If I have a honey molecule, very bad language I'm using right now. It should not be called honey molecule. Okay. The molecules in honey, no, there are very huge degree of cohesive force, but water will also pull, but the cohesive force will be less. No, water doesn't like to pull so much another water as compared to your honey pulling another honey molecule. Okay, very bad again, not honey molecule but the molecules that are present in honey. Okay. Okay, in short, okay, what we are trying to tell you, okay, see, the flow of a liquid is decided by the stickiness. Okay, I'm going to use this word, okay, right now, stickiness. This stickiness is what we call it as viscosity. Viscosity, it is like stickiness, okay, stickiness of the molecules towards each other. Okay. And when we consider that in terms of flow, this can be imagined. Okay, please check. I think you will understand what I'm trying to say, so just give me 1 second. Okay, see, so let's quickly compare the flow of water first. Okay, then I'll come back to your honey. No, so see, so what basically happens, okay, see, this is the bottommost layer of water. Right now this is water. This is the bottommost layer of water which wants to flow towards the right, because our whole liquid is going to the right. Okay, don't think it is a closed container here, because I have drawn it like that. Don't think it's closed. This is going to continue. Okay, it's going to flow and flow and flow on the right side, towards the right side. So just check. Okay, I'm going to mark one layer exactly just top of your bottommost layer. Okay, or let's say bottommost surface, because it's a liquid, right, it will need another surface, no, to move on to. Okay, so this is red one represents the bottommost layer. Okay, bottommost layer of water, and this bottommost water of layer of water, let me tell you, okay, it can be imagined to be at rest. Does it make sense? Did you understand what I said? Though our liquid or water, right, is moving to the right, it is moving. Okay, but if I go from the top to bottom, okay, let me tell you the speed of all these layers that I'm trying to represent here. See, every liquid flow, no, can be treated as if one layer of molecules, then the molecules below it are just moving on top of the another layer, right? There's no solid here. If you notice here, see, there is no solid here. This is not solid. These are not solid. These are all liquid molecules only. Okay, and the molecules above it are also what molecules? They are liquid molecules. And you know what? All these molecules, right, they can be imagined to be composed of they form the first layer or the topmost layer there, and just below there we have another layer which is also going to move forward. We have layer below it. We can imagine like that. Okay, one liquid layer moving on top of another liquid layer. Do you understand what I'm trying to say here? This is how we, or what we call it as a flow. Is it okay? Did you understand this?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so all these molecules that I'm drawing, right, below and below and below, okay, so they are moving, of course, with some speed, but the point is this. Okay, this is found to be this. Okay, say the topmost layer, okay, that is this one, right? Okay, it is not in between two layers of liquid. It is just above one layer of liquid. Okay, but however, if I look at any other layer, this one, right, this layer, this layer is in between two layers of liquid, that is this and this. Let me just show you. It is between this layer and between this layer. Okay, I'm talking about this middle layer. I'll show you again. This middle layer, okay, this one, it is moving in between another two layers, and that is this layer, and I showed you this layer. Okay, so but the topmost one, right, is not between two layers. It is just above one particular layer. Okay, and it is found that the topmost layer moves the fastest. Does it make sense? Moves the fastest. It is observed like that. Okay, you may ask why and all, but no problem. Okay, but for the time being, I'm just going to say that it moves the what? Fastest. The layer below it is found to move slower. It is not at the same speed. The layer below that is much more slower speed. The layer below it much more slower. The layer below it much more slower. If I keep on going down and down and down, and as I reach the bottommost layer, right, where I also have another set of liquid molecules, which I can show you right now here, like this. Okay, let me just show you here. This is the bottommost layer of the liquid. Okay, liquid molecules or water molecules in this case. No, they are considered to be at rest because they don't have any movement. Okay, so we don't have any velocity there, so we can imagine it to be at rest. Of course, they'll be moving little bit here and there. Okay, but as a whole layer, okay, they don't move. As a layer together, they are not going to move. I'm repeating again. Okay, so I'm going to ask you. Okay, see. So what did you learn just now? You know, this is what you have learned. See, which is true for any liquid that I'm talking about. Just let me show you one more time. Then I'll come back to the main part. Okay, see. So what did you learn, guys? I think you have understood, at least something you have understood. Okay. By the way, when you sit on top of a river also, right, and imagine the river is flowing. Okay, imagine the river is flowing in this direction. Okay, what do you think? If you are here, if you have a boat and the boat is here, okay, what do you think? The boat will move fast or not, or the fastest? The boat will move fastest. Okay, because the boat is on the topmost layer, and the topmost layer travels the fastest. For any liquid that happens. Okay, what about the layer here, guys? Moves the same speed or slower? Slower. Okay, that is what I was talking about. And the layer, right, which just above the solid contact, okay, does not have any speed. The velocity here of this layer is equal to be 0. Okay, are you clear with this scenario or scene? Are you clear with this idea?
Yes, sir.
Okay, so the fastest layer, you know what happens, right? Now let me ask you, okay, if I start measuring the distances of these layers, right, because I can imagine the whole liquid flow in terms of layers. So if I ask you, okay, what is the distance of this layer from the bottom, right? Your answer is x equal to how much? 0. No distance. What is the distance of this layer from the bottom? It has some distance or not? Let's call it x. Are you clear what is x, guys? Distance of this layer, right? Yeah, distance of this layer above that bottom layer, the bottommost layer, right, which is at no speed. Okay, so if I go on moving top and top, right, above and above, okay, I told you are going to notice that the layers become faster and faster. So if I just take, okay, just think about this. Okay, right now this particular layer, okay, is having a velocity called what? V. I think you're clear with that, right? Maybe 30 meter per second, 20 meter per second. Okay, and you know what, just above this, say just above this, right? Okay, very very near. Okay, I'm drawing it far, but you have to understand it's not very far, it's very very near. Okay, can you tell me, guys, how far is this next layer that I've drawn? Do you think it's very far or very close?
Very close.
Very close. Okay, so how much will be the value of the gap between these two layers, between this layer and this layer? What is the gap? It will be called x or dx? dx. That's the gap between these two layers, and they are very very close. Okay, what do you think will happen between these two layers? Okay, they will have same velocity or different velocity?
Nearly equal velocity.
Nearly equal.
Almost equal.
Okay, almost equal. Okay, I will take that. But can you tell me who will have slightly little more velocity, the layer above or below?
Above.
Above. Okay, yes. Okay, so I'm going to write here something. Look here, I'm going to write here v plus dx, because it's going to be more than the layer below it. Okay, so that layer is going to have what? V plus dx. Okay, what about the layer below, guys? Okay, I can also imagine another layer. I can show you here, which is just below and little bit below, not so much, right? So what's the gap again, guys? How much is the gap?
dx
Again. Okay, makes sense, no? What will be the velocity of this layer? You tell me now. It will be v or less than v?
v minus dx.
V minus dx makes sense. Okay, this is going to be velocity. This will be for that, this will be for that. Okay, so I think you got my point, what I'm trying to tell you, right? So you know what, I can write a term, okay, which is very very important for us. Just check whether it makes sense or not. I'm writing here dv by dx. Does it make sense? What is the meaning of dv by dx? Or let me ask you from the beginning, what does velocity depends on what in this case?
So velocity is a function of displacement.
Very good, very good. Okay, displacement, or let's say, yeah, displacement also you can say that. Okay, depends on what? On x. Do you agree, guys, with that? Because you know what, because when the velocity, when the displacement from the bottom layer is how much? 0, then the velocity is also how much? Here 0. If I go up, the value of x keeps on increasing or not? If I go up, yes,
sir.
Yes.
the velocity, the x keeps on increasing, and after whatever I have talked, right, also you have learned, right, that even velocity will increase. That means as the x changes, the velocity also changes. So what is this quantity, guys? What is this? This is velocity or change of velocity or rate of change of velocity?
Rate of change of velocity.
Okay, but it is a time rate of change or it is a rate of change of velocity with displacement?
With displacement.
With displacement. We have a very nice name, okay? We don't read it like this, okay? We have a name for it, okay? The change of this velocity with distance, right? Or anything, right? With distance, we call it gradient. So this is like gradient, okay? Gradient. And we have another name for it, okay? We call it very nicely, we call it velocity gradient. Don't worry, you will understand the moment I start speaking or giving you this example. See, guys, let me come back to this. Don't worry, I think you got the point. So this layer has a particular velocity, this layer below it has a slower velocity, the layer above it has more velocity, and that's why I told you, right, the velocity here is v, the velocity is v plus dv, the velocity here is v minus dv, and the gap between the layers is dx and dx. And the bottommost layer, the velocity, okay, is not there, so it has 0. This is the topmost layer, the velocity is how much? Maximum. Till now you understood, okay? And I told you, right, as I go up and up and up, okay, so at a particular layer where the velocity is the position is x, it has a velocity of how much, guys? I'm repeating again. At a particular layer, right, any layer which is like this, what is the velocity of this layer, guys? It is v. The position of that, we are calling it what? X. So it can be any layer, you decide. If you want to say x equal to 0, I'm talking about the bottommost layer. If I talk about x equal to maximum, I'm talking about the topmost layer. So x decides, right, okay, velocity of which layer I'm talking about, okay. Now, just now I told you, okay, so think and tell me, right, I told you that velocity is a function, okay, it's a function of what? X. If the x changes, x is 0, velocity also 0. X increases, velocity also increases. That's why I wrote this one, see. So now there's a change of velocity with what? There's a change of velocity with x. That's why we wrote a very nice quantity I told you just now. We call it what, guys? dv by dx, and we have a name for it, okay? You already told me, not you already, I told you. What is that? We call it velocity gradient. Velocity gradient. Okay, now check something, okay? Now we really start. Imagine I have a velocity gradient, okay? 10 meter per second per 1 centimeter. Just an example, very bad, but it will work. 20 meter per second, I'm giving another, per 1 centimeter. 30 meter per second per 1 centimeter. Okay, now think and tell me, what does this, the first one means, indicates? That means the velocity is going to change by how much?
10 meters per second.
After how many? For every 1 centimeter. Very good. Okay, I'm going to give you one very nice example and you think and decide whether it makes sense or not. Okay, look at this, guys. See, actually, basically viscosity, we really have to discuss it like this, okay? We have to go slow and keep on talking and talking and talking till you form the concept. Just check. Okay, again I'm going to start. See, so v is how much? Let's say 100 meter per second. So this particular layer, okay, and the gap between the upper and the lower layer, okay, with the middle layer is 1 centimeter exactly. Okay, this is the gap. Okay, this is the gap between the two layers, above and below. Okay, so now if I tell you that this is the velocity gradient, okay, tell me what will be the velocity of the upper layer, guys? Is it going to be 100 or more than 100?
More than
100. How much more than 100? According to what I wrote here, it should be 10 meters per second faster after every how many centimeters?
1 centimeter.
That means if I go above this layer, if I go above this layer by how many centimeters? 1 centimeter, it should be faster by 10 meters per second. That is the meaning of this velocity gradient. All these are dv by dx values. Okay, so think and tell me now, what will be the velocity of this layer? 110 meters per second. Okay, did it make sense, guys, to all of you? Just check.
Yes, sir.
Waiting. Daphilin is there.
Yes, sir.
Sangam is there. Bhabok is there. Okay, many are not here. Polom is there. Prayash is there. Okay, then look at the below layer, guys. Now tell me, below layer, what do you think? Will be 100 or less than 100?
Less than
Less
and,
than
every 1 centimeter I go down, it should change by how much? It should change by 10 meter per second.
10 meters.
So it should be 90 meters per second. I think you're clear with that. This part is clear. This part is clear. This part is clear. Okay. Now let me tell you why there's a difference. Okay. Till now I did not talk about why there's a difference in the value of the velocities. Okay. Let me use blue. Okay. Now see, I'm still talking about water right now. Okay. Very bad. I did not use exact numbers, but no problem. It will work. Okay. See. Just check. Okay. See. I have water molecules here. Let me use a lighter color. 1 second. I have a water molecule here, 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 here. Okay. All these molecules are in contact with the molecules above it. All of these molecules can be treated as if they are moving in layers. One liquid layer moving on top of another liquid layer. We all have these molecules. Okay. Now basically I'm really not talking about the force between molecules after 1 centimeter. That I should not do. Okay, but I should talk about force between molecules which are just in contact above it. Okay, the force. I hope you understand. I really want to talk about the force between the molecules above this particular layer and below this particular layer. There are molecules, not after 1 centimeter. Okay, that comes later. Okay, now you think and tell me. Okay, do you agree that what somebody said earlier? Okay, honey is sticky, right? Okay, and water is not sticky. Do you understand that this particular layer which is at 100 meters per second, and all these liquid molecules, they want to move forward. Okay, what will the molecules below it try to do? Or let's say, what will this molecule try to do to the below molecules, or the molecules which are below it? They have some degree of attractive force or not?
Yes.
So this particular layer, okay, this one, the molecules here, right, they want to move forward, right? But the molecules below it, right, they are not moving forward at the same speed. Okay, it's like this particular layer is going to drag. Okay, is going to drag. I'm repeating again. This particular layer of liquid is trying to drag the molecules below it. Can you understand this? How will I explain to you this? I think you did not get me. Imagine, okay? Imagine this is what? This is a very bad example again, okay? These are flowers, okay? These are flowers. Very bad example, okay? And I don't know, who will I bring? These are flowers, okay? Flowers, petals, very light petals and all. Who do I bring? Let me bring Viswasdeep, okay? So Viswasdeep is going to fly. No, he's going to fly, okay? Viswasdeep is going to fly. This is Viswasdeep, okay? He's a what? I'm trying to draw him like a witch, okay? In a one, no? I think you can understand my diagram, right? Okay, so yeah, like Harry Potter, exactly. This is Viswasdeep Potter, okay? Okay, what do you think will happen, guys? Tell me. As Viswasdeep tries to go front, right? This green flowers will be attracted to him, okay? Let's say there's some degree of attraction, right? Tell me now what will happen. Can Viswasdeep really move forward, or he will be slowed down?
Sir, it will obstruct the motion.
It will obstruct the motion because look, Viswasdeep is trying to flow, go front. He's trying to go. But because the flowers are pulling him, right? So can he move forward just like that, or his motion will be disturbed?
Motion will be
His motion will be disturbed, okay, by the molecules which are below it. But he is going to move forward, right? But do you also agree that the below molecules are also moving, right? Yeah, they are moving, okay. And you know what? But still, the molecules below it will disturb his motion. Will not want him to go forward at his usual pace, because they have attractive force between them, as Soumitra said earlier. No, they have cohesive force. Okay, I think you are clear with this part at least. Okay, so just think and tell me. Okay, the motion of this particular layer, right? This particular Viswasdeep layer, okay, is disturbed or not?
Yes, sir.
Okay.
Yes, sir.
Is this layer of liquid molecules facing some obstruction to flow or not? And what will be the obstruction direction, guys? It will be towards the right or left right now. The direction of flow is towards the right. What is the direction of obstruction, guys? Towards the right or left?
Left.
This is the direction of force acting, okay, on towards the left, okay, on this particular layer we are talking about, okay. So now this force, right, it is just like friction. Can you understand? It is almost like what? Like friction, but you can be very clear, it is not friction, it is friction in liquids. And this friction in liquids is known as what? We call it viscosity, not viscosity, okay? There's no city here, okay? Viscosity. Can you understand what I said just now, guys? Don't worry, I can just talk about like this only, okay, this topic. But did you understand what I said just now, guys? Okay,
Yes.
just think like this, okay?
Yes, sir.
Just think, okay? All these molecules, they want to move forward. They want to move forward, but your molecules below them, they attract, okay? The molecules are attracting. So even if the molecules above it, they are moving forward, okay? They'll not be moving forward with this usual speed they should move, okay? Because the molecules below, right, will try to pull them and try to drag, okay? The another word you can use is drag. Okay, not drag in the forward direction, but drag them behind, okay? Because it's like they are hanging here. All these are hanging here, see, like that. It's not that they're really hanging, okay, but you can imagine like that, okay? But that is what I want to tell you, okay? Now just try to think, okay? I'm going to change now, okay? Imagine if I go from this velocity gradient to this velocity gradient, think what will happen, okay? Think, okay, nicely, and tell me, huh? So do you understand, guys, till now? The velocity gradient I've used all these numbers, right? Is how much velocity gradient for this one, and this one, guys? How much? 10 meter per second is the change of velocity per how many centimeters?
1 centimeter.
1 centimeter. This is the velocity gradient I have chosen between these layers. I'm going to go now to 20, okay? Think and tell me, okay? See, suppose I tell you now, this layer has a velocity of 100 meter per second, okay? Then what will be the velocity of this layer, guys, after 1 centimeter? If I consider the velocity gradient to be how much now? 20 meters per second after every 1 centimeter. So now tell me, guys, how much?
120 meters.
120 meters per second. And the below layer will be how much, guys? The below layer, which is below it, it will be 80 meters.
8 meters per second.
Because after every 1 centimeter, the velocity should change by 20 meters per second, okay? I'm going to compare only these two cases. I think it will be fine. This is case A and this is case B. Please tell me in which case you have more velocity gradient, A or B? B. B, you have more velocity gradient. That means the moment A or B? Somebody said A.
Oh, sorry, sir. B.
B.
I said velocity.
So now is the time to ask you, okay, in which case do you think we have more opposing force? In which case we have more opposing force? Think and tell me.
So B.
A or B? In which case we have more opposing force?
So B.
B.
A. Sangam said A. Okay. Answer is B. Okay. I'll tell you why. Think, okay. I know you are thinking in a different way, but think like this, okay. Look at this. This layer is moving at 80 meters per second. This layer is moving with 100 meters per second. What do you think? The layers are really allowing this liquid to move faster, or they are obstructing it more? Or the molecules above? Just in 1 centimeter, look at this. Just in 1 centimeter, the velocity has changed by how much? 20 meters per second. And in the first case, you know what? Just in 1 centimeter, just after moving 1 centimeter above or below, right? The velocity changes by how much? 10 meters per second. Okay, I can give you one more example, okay, very quickly. I think you'll understand, okay. This is 100, by the way, this is 90, huh? Imagine, I have two layers like that. He's also moving with 100 meters per second. He's also moving with 100 meters per second after 1 centimeter. Who can tell me what's the velocity gradient, guys, in this case? What's the velocity gradient?
0.
0 meters per second after every 1 centimeter. That means after going up or down 1 centimeter per centimeter, right? Still there is no change of velocity. Now you think, are they really obstructing or applying opposing force, or not applying any opposing force?
No opposing force.
No opposing force.
No.
Do you understand this? one layer does not oppose the motion of the another layer. That's why the speed of all the layers is what? Same. So there's no opposing force. So is there viscosity or no viscosity?
No viscosity.
No viscosity. Okay, so when there is no velocity gradient, please remember this. If there is no velocity gradient, that means what? The liquids have any viscosity, no viscosity? The answer is no viscosity. Okay, they cannot, they don't apply any opposing force. Okay, but look at this now. What do you think? Let's compare now again. Okay, this is 100, this is 80, this is 100, this is 90. In the case A and case, okay, I've changed over. Oh yeah. No, where was I? Oh yeah, this case A and this is case B, no? Oh wait. Sangam said A, right? Earlier. Which one's case A?
Yes, sir.
Very good. Okay, Sangam is right. In which case we have more viscosity. Now think. A or B? Now what is your answer?
Sir, which one is A and B?
This one is A right now. I don't know. I think I confused you already. Okay, maybe. Okay, but this is B now. Okay, now you can answer again. Yes. In case A or B, we have more opposing force.
Sir, A.
In A, yes, we have more opposing force here. More. Why? Simple logic. Because one layer is so good in reducing the speed of the other layer that just by going 1 centimeter, the speed of the other layer changes by how much? By 20 meters per second. Okay, and in the second case, one layer is not so good in reducing the speed of the other layer that by going 1 centimeter, it changes only by how much? 10 meter per second.
10 meters per second.
But I think you understood. Okay, so what did you learn just now? You know what? I tell you, you have learned something that there is called an opposing force. Okay, there's an opposing force between what, guys? Between molecules or between layers of molecules?
Layers of molecules.
Between layers of molecules. Example in what and what? In fluids and in fluids. That's your liquids and gases. Okay. Yeah. And this opposing force, I already told you, right? What do you call it?
Viscosity.
Viscosity.
Okay,
this is a property called viscosity. The force can be called as viscous force, and it's acts between the layers of the liquid. Okay, that means this layer wants to move, the other layer is below it, doesn't want to move so fast. Why? Because it experiences some attractive force. Okay, so it doesn't allow the other layer to move faster. Okay, that is what is happening here. Okay, not only that. Okay, do you agree that this is exactly like or somewhat like friction? Can I call it friction?
Yes, sir.
So friction in which case, guys? In friction in liquids and
Liquid.
liquids and fluids. No, liquids and gases.
Gases.
Okay. In gases also it happens. Okay. Then what else you learn, guys? There's something called what gradient I told you? Velocity
Gradient.
If velocity gradient is 0, means what? This opposing force is there or no viscous force?
No viscous
Nothing.
force.
Okay, nothing. Okay, no viscous force. Okay, then what else you have learned just now? This viscous force, I need to write something more about it. Okay, imagine I have now, this is the topmost layer, by the way. Just let me draw it again, redraw. Okay, this is the topmost layer. Okay, see this one. I drew only one chain, but I have another chain here. No, see, like that. Okay, very bad diagram, I know, but let me just draw it. This is the layer below it. See this one, this is a layer below it. Okay, now you think and tell me. Okay, imagine a diagram which looks like this, and this liquid molecules, they want to flow. And I have another diagram. Okay, check. I have a very big area like that, very big area. Right now, talk in terms of area of these layers. Okay, so this is the first layer, the topmost layer. I have this topmost layer trying to move on top of a layer which is below it. Okay, but this time, what do you think, guys? We have same area or bigger area? Area A and area B. Which one is bigger? A or B? I think I made it clear. No? B is bigger. Okay. I really want to draw A smaller, huh? So A is small and B is a bigger area. Okay, now think and tell me. Okay, in which case you tend to get more cohesive force between the layers, in a layer which has smaller area or a bigger area? More cohesive force total. Okay, more cohesive force, attractive force. Which case?
Bigger area.
Bigger area, yes. Bigger area shows that the layers, okay, because see, okay, you cannot say that only one molecule is going to move. You have to treat it like the motion of the whole layer, okay, for fluids, okay. So you cannot just say that one molecule, two molecules will move, right? It is the whole layer that we are considering moving. That is how we should visualize the flow of liquids in terms of layers, not just one, two molecules like that, okay. That's why, you know what, the area plays a role, okay. So now you think and tell me, okay. More cohesive force, you already told me, in bigger area. That means what? The opposing force that we are talking about, right? The opposing force from one layer applied to the other layer, right, will be dependent on area or not. The viscous force, let me write F. It depends on area or not, guys. Just think. Yes, waiting.
Yes, sir.
Will
Yes.
depend on area, okay. What else force depends upon? I've already told you, force also depends on what? Velocity gradient, not on velocity, okay. The force, the opposing force, this is viscous force, opposing force, just like friction force. Let me write friction for the time being, okay. It's like friction in liquids, no? So it depends on velocity gradient, depends on area. Now let me ask you, okay, what else do you think it depends upon? Does it only depends upon the velocity gradient and the area, or it also depends on the nature of the liquids?
Nature of the liquid.
Okay, if I compare this layer, okay, these two layers and these two layers, okay, same area, same velocity gradient, okay, but this is water, of course, and this is honey, okay. Now you think and tell me, okay, here the liquid layers will move, here also liquid molecules will move, here also they will move, here also they will move, okay. In which case do you think we are going to get more opposing force, honey or liquid? Oh, sorry, honey or water, what am I saying?
Honey.
In honey we get, okay, that means what, you know, this viscous force also depends upon what? Depends upon
Nature.
nature
Nature of the liquid.
nature of liquid, okay. Now one more thing I want to ask you, okay, what is the direction of this force that we are talking about? It depends on the nature of the liquid. This viscous force is more in honey compared to water, as I told you, okay. But I want to ask you one more thing. Depends on nature of liquid, but yeah, what was I about to say? What happened to me? I've forgotten so many things. I was about to say something. Oh yeah.
Direction.
Okay, yeah. What about the direction of this force, guys? What do you think?
So it's always opposing.
Okay, direction of this force is opposing, okay. I have a word for that, okay. We can call it tangential. What is this word called? Tangential, okay, because this is the layer and the force will act in this direction and the layer wants to move in this direction. Tangential, okay. But friction is a bit different, do you realize? Friction is a opposing force, obviously, okay. But how do we write friction? You know, the static friction or the kinetic friction depends on what? Normal reaction, okay. If there's a force acting on this box, then you know what? This is the normal reaction, right? And what is this? Weight of the body, yes, okay. Yes, the friction will oppose the motion, okay, but friction will act because of what? The friction acts because of normal reaction. That means frictional force is in which direction? Normal, or let's say okay, that's how it obstructs this motion, okay, but the direction of friction is normal, perpendicular. Can you understand the difference between friction and this one, viscosity? Can you understand the difference?
Yes.
Okay.
Yes, sir.
Here the nature of the liquid, here it depends on the nature of the two surfaces in contact. Friction is, however, a normal force, but this viscosity is what force, guys? Tangential force. Okay? Tangential. It's not like that, okay. It's not like that. No, it acts tangentially, okay. Then you know what? One more thing, okay. Does friction depends on area or not? Never.
Yes, sir.
No.
Oh,
friction
like,
doesn't. No, friction never.
viscosity.
Friction never depends on what? Area. It depends on normal reaction, but who depends on what? Viscosity depends on area. Okay. It's an opposing force to the flow of liquids, but you got so much idea, okay. Now let me write it down. See. So viscosity, the viscous force that we are talking about is equal to, let me write a constant, okay. Let me write a constant. I've removed the proportionality sign. I want to write F is proportional to area. I want to write F is proportional to dV by dx. I want to write F is proportional to nature of liquid, but I cannot do that, nature of liquid. But this is not possible because I'll tell you, this is not a number. It's not a number. So you cannot write, area is a number you can write because force is a number, area is a number, measurable quantity, dV by dx is a quantity, but nature of a liquid is not a number, okay. To represent the nature of the liquid, we bring a constant, that will be a number, and that will represent what, guys? That will represent nature of the liquid. Did you understand what I said? I think it did not make sense to you all.
Sir, nature of the liquid and density is the same.
No. Density and nature of the liquid is not same. Okay, some liquid may be dense, but maybe offer very less viscosity. You understand? Okay, so that's why it's not like that, okay. So basically what I'm trying to tell you is this, guys, see, okay. I told you, right, the viscous force or viscosity I'm talking about depends on area, okay. I'm going to write that. It's a measurable quantity, is fine. dV by dx represents velocity gradient, that's also correct. Depends on nature of the liquid is also correct, okay. But the problem is, in a formula you cannot write what? Nature of a liquid, because it's not a what? It's not a
It's not a number.
It's not a number, not going to make sense. That's why what do you bring? In place of nature of liquid, we bring what? A constant. And yeah, this constant will tell us about what?
The nature of the liquid.
The nature
The
of
nature of the liquid. You will understand the moment I complete this formula. Okay, so whatever is constant, just let's check. Okay, so I'm going to write here dV by dx. Okay, and I'm also going to write area. I'm going to put a minus sign just to show that it's an opposing force. It destroys motion. It deaccelerates, no? The layer, okay, the layers, okay. So that's why we have this minus sign in front, okay. This constant I told you, right, depends on the nature of the liquid. That's why we have written it. Let me complete it, okay, check now. F equals to minus eta, I am going to write dV by dx into A. This eta, we have a name, we call it coefficient of viscosity. Now I don't have to talk much, okay, because everything is there right now, sitting with us, okay, because this will help us with everything. Now you think and tell me, okay, which kind of liquid, okay, one by one, okay, which kind of liquid layers will try to have more opposition, guys? Liquid layers of big area or small area?
Big area.
Big area. Greater area, more opposition to the flow of each other, okay. It's not just one layer, flow of each other, okay. Each layer will flow at slower speeds, okay. It will reduce, the one layer will reduce the speed of the other layer if they have big area. That's what this is all about, okay. Then which kind of liquids I will say that they have more viscous force or viscosity? If they have velocity gradient or larger velocity gradient?
Larger velocity gradient.
Larger velocity gradient. I showed you one layer moving at 10 meter per second, one layer moving at 20 meter per second just after 1 centimeter. So what's the velocity gradient, guys, in this case? How to calculate? Tell me. Waiting. How much is velocity gradient? dV by dx. Change of velocity is how much?
10.
10 meter per second.
10 meter per second. After how many centimeters? Dx means centimeters.
1 centimeter.
That is the meaning of velocity gradient. I think you are clear with this. Plus minus depends upon which layer we are talking about. Okay. And finally, please tell me, what is this eta? Why it is there in this formula? Because the viscous force not only depends on velocity gradient, not only depends on what? The area, but also depends on
Nature of the
yes. And this nature of the liquid is entering as what? We call it coefficient of
viscosity.
Coefficient of viscosity. Okay, fine. Coefficient of viscosity. Okay. Now you think and tell me. Do you agree the way it is that I've written, right? I've written eta directly. If eta is large, what is it trying to say? That means the nature of liquid is such that, or the fluid is such that, if eta is large, it represents it is having a viscous force, a very high viscous force. Large eta. Directly proportional, right? Yeah. Large eta means a viscous force which is large. Okay, now I can go to the nature of liquid. Nature of liquid means the type of liquid actually I'm talking about. Okay, so please check. I think we'll understand. I'm going to start with water. I'm going to write a number. Okay, eta for water. Okay, because it is water, it has some value of eta equals to 1. Okay, Pascal second. I'm just copying this number right now, but at the temperature of 20 degrees Celsius, don't worry about these numbers right now. You will understand the number, okay, the moment I write for another one. Look at this. I'm going to write for blood, okay. Look at this, blood. Actually, I should mention temperature also, but right now I am just writing 37, 37. eta for blood at a temperature of what I'm doing, at a eta for blood is 0.3, okay. Will it be less than 1? No, 2.7, okay, Pascal second. Don't worry about the units right now, but this is the temperature of 37 degrees Celsius inside our body. They have calculated, okay. Just let's look at this two numbers first of all, okay. Can you understand? I've already written a number corresponding to what and what? Water and blood. Think and tell me, okay. Where do you think I'm going to expect more viscous force, in blood or water? More viscous force.
Blood.
Blood. This number is just exactly trying to tell me that we have to get more viscous force in blood compared to what, guys? Water. Water. You can easily imagine now. Tell me, which one flows better? Which one tries to stop the other layer less? It's water, right?
Water.
Okay. Blood is not going to flow like water, okay. If your blood will start like flowing like water, okay, your heart really has to beat, I don't know, 500 times per second maybe, no? This is what I'm trying to say. Not 500 times, this is 300 times. Per minute. Your by the way, your heartbeat is how much? Normal 72, I think, no? Beats per minute. Did you understand what I'm saying? If
Yes, sir.
the viscosity of your blood is less, what does it mean? The blood will flow very fast.
Flow faster than water.
Flow faster, okay, not like usual blood, but it will flow faster, and your heart will have to pump blood, no? Has to pass oxygen, right? It has to do at 72 beats per minute or more beats per minute.
More beats.
More beats, okay, because you can understand, I think. I don't know, okay. I'm going to biology right now, but not important right now. But the point is what? I think you can understand what this number automatically tells you. What you can already guess what kind of motion they will have, right? I'll give you another example. Honey, okay, let me write honey. Honey, the viscosity, okay, the viscosity of honey, okay, is around, just check at this, okay, 200 Pascal second per at a temperature of 37 degrees Celsius, okay. Okay, now check. Can you imagine honey and water now? The value of viscosity is same, or for honey it is 200 times more?
So it's 200 times more.
200 times more. So what is going to happen? What is the meaning
So
of...
water will flow 200 times faster.
No, it's not about faster. Okay, he is going wrong. It's not about 200 times faster. Who can tell me? Viscosity of honey,
So
right?
like the viscous force will be 200 times less in case of water.
Very good.
compared
Yes.
to honey.
He's right. Okay. Did you answer what he said, guys, just now?
Yes, sir.
Okay. The viscous force in honey will be how much? The opposing force, right? Which one layer of honey will apply to the other layer, right? Will be 200 times the viscous force one layer of water will apply to the other layer. Can you understand? Does it make sense now? Does this number make sense?
Yes, sir.
Okay, so now you can easily tell me, right? The flow of which liquid is not going to be so good, no? It doesn't look like very nice to, right? It's honey, right? Okay, and water, right? Because opposing molecules are not applying so much opposing force, right? Okay, what I'm saying, the layers, right? The liquid molecules in those layers, they will not apply so much opposing force in water, but they will apply 200 times more opposing force. Okay, you can understand that Harry Potter, Visudeep, okay, was somewhere, I don't know where I drew him, okay. Imagine a very high viscous force. Now you tell me, this Harry Potter will move and will be very difficult to move.
Very difficult.
So I'll
Very
be stuck.
very difficult to move because, okay, yeah, because the opposing force is very high, okay. But I think you got the point, okay. So, okay, now let me define to you what is eta, okay. Because of that, I need to write the formula again, okay. Now, we really have, I think, understood at least the idea behind this number, right? Eta, coefficient of viscosity. Are you
Yes.
clear with the number, guys, at least?
Yes, sir.
What does it mean? What does it mean to talk about higher eta, lower eta, very high eta and very less eta, right? I think you understand coefficient of viscosity, very high or low. What does it mean? Okay, let me go back and let me write the formula. Please tell me, guys, what does viscous force depends upon, guys? Nature of the liquid,
liquid,
So I write eta
Area and
velocity
gradient.
gradient and then
and
area. Is it same like friction or not same like friction?
not same.
Not same. Okay. What is not same? Area.
It's technical.
Okay.
Doesn't depend on area.
Friction doesn't depend on area. Very good. Moreover, this is what kind of force? Tangential.
Force.
But in the other case, it is normal force. Okay. At
Normal.
least you know some differences. Okay. Obviously. Okay. So now it's fine. Okay. Now check something. I want to define what is eta. I have already given an idea about what is the meaning of large value of eta. You know what does it mean? You know what is the meaning of small value of eta. I'll just come back and tell you something more. Okay, look at this. Do you know what's the meaning of large value of Young's modulus, guys? Young's
That it's more elastic.
Young's modulus for steel is greater than what? Young's modulus for rubber.
Rubber.
That means steel is more elastic than what? Than rubber. Yes, steel is more elastic than rubber, right? They tell you these numbers. They tell you about the material, more elastic or less elastic. Okay, I'll tell you another one. Okay, yes. Oh yeah, coefficient of static friction for wood. Okay, for wood and wood is greater than coefficient of static friction for ice. What does this numbers tell you? That the opposing force in ice will be what? Less. Opposing frictional force will be less, right? In ice and ice compared to wood and wood. Okay, we know this. See, we just have to know these coefficients. Okay, they're very nice. This is also actually a coefficient. Okay, then what else? Tell me, guys. Have you ever heard about anything else?
So resistance.
No, not resistance. Anything else? Which tells you the property of a material. Okay, imagine I have a property called thermal conductivity. Have you heard about that?
Yes, sir.
Thermal conductivity of copper. Thermal conductivity of copper is very greater than thermal conductivity of wood. What does it mean? What do you think? Already you can understand. Who conducts heat more?
Copper.
Copper compared to wood. Yeah, obviously, right? Okay, that's why we have copper cooking utensils. Okay, or maybe I don't know other metals. We don't cook in wood. Okay. Then do you understand, guys? All these coefficients, right? They tell you about the material or not, because all the materials have different properties. Coefficient of thermal conductivity for copper is greater than for wood. It conducts more heat. Coefficient of static friction is more in wood compared to ice. That means ice will offer less friction. Young's modulus for steel is greater than what? Rubber. That means steel is more elastic. Very difficult to stretch steel. That is another way of talking it, right? Okay. And one more last thing we have learned today. What? The coefficient of viscosity for whom? Honey is larger than what? Coefficient of viscosity for water. What did you understand? The moment I tell you, what did you understand, guys? That means the obstruction between the flow of layers in those liquids, right? We get more in what? Honey. Okay. So do you understand? Yes. Okay. So, but I think you understand, right? Every time we are always going to get this kind of coefficients, okay, and they tell you about the nature of the material, okay, or whatever we are talking about. Okay, now say, so once we are done with that, let me just define to you very quickly. Okay, if I write dV by dx equals to 1 unit, I think we can understand this. And if I tell you that area is also equal to how much? 1 unit. Check. Okay, then my formula for F will be equal to how much? Minus eta. Do you agree with this? Just check. Right. Because you know what? I just made this entire thing. Suppose if I tell you it's 1 unit, we can just read it 1 unit of velocity gradient. 1 unit of velocity gradient, and area is also how much? 1 unit. If I make these two things 1, 1, 1 and 1, then automatically your F will be equal to what? Minus eta, right? Then I can write your eta will be equal to what? Minus F. Or I can simply write eta is equal to, okay, the magnitude. Let me just write, okay, eta equals to F. So do you realize that if I, under these conditions, okay, under this one and this one, you know what we have got? We got a definition of eta or not? Now you tell me, what is eta? What does it look like from here to here? What is eta? Okay, first of all, tell me, what am I trying to define? I'm trying to tell you what is the meaning of this number. Till I did not tell you exact meaning, okay, but you already know what does it signifies, okay. Now tell me, what is the definition, guys? What is eta? What does it look like? Eta looks like what? Equal to what?
It is the force.
Very good.
required.
Coefficient of
Viscosity.
viscosity. It is the what?
is the force
Ah.
required
Is
to
the
move,
force required to what?
uh,
To
to
maintain
move or to maintain
a unit
velocity
The
gradient
velocity
at
gradient
unit
of unit area. Very good. Now let me just write it down. Okay, let me try to explain. Okay, maybe I'm not speaking so well. Okay, but just check. Okay, guys, see. Okay, eta means nothing but f. Think. Okay, think. Do you agree that I want this layers to have one unit of velocity gradient? That means dv by dx equal to how much? 1 unit. Does it make sense? Just check, guys.
Yes, sir.
And the areas, okay, of these two layers,
Yes,
no, that I'm talking about, the area layers is how much? How much is the area, guys? 1 unit.
1 unit.
Do you agree that there's an opposing force? Yes. This opposing force is nothing but what force? Viscous force. Okay, now you think and tell me. Okay, do you agree that, okay, under this condition your eta will be f, right? Check. Your velocity gradient is how much? 1 unit, and your areas are also 1 unit. Okay, do you agree that we should apply force in this direction, right? And this force that I'm applying, right, will oppose this viscous force or not?
Yes, sir.
If there's a force towards the right, I'm repeating again, if there's a force where, guys, towards the right, then there will be a viscous force, and this force, right, whatever I'm talking about, okay, is going to what? Is going to oppose, right? Is oppose our which force? Viscous force. Okay, 1 second, I need to pick this call. 1 second. Hello. আচ্ছা আচ্ছা পাশে কত পারেন না কি হলো এখন পাশে কত পারি মা তো আসতে আসে পাশে কত পারি না okay, so sorry. Okay, guys, okay, you did not understand this one. Okay, say, imagine the bottommost layer. This is the bottommost layer. Okay, guys, just give me one try with this one. Okay, say this is the bottommost layer, right? Please tell me, guys, what is the speed of this layer? Speed, velocity, how much? 0. Okay,
0.
okay, look at this. This is the topmost layer. Right now it is also not moving. So is there any opposition from the layers or no opposition? No opposition. So it is also v equal to 0. The moment this top layer, which is, let's say, at 1 centimeter apart, okay, just let me make it 1 unit. It's like talking about 1 unit only. Okay, 1 unit area is already 1 unit. Okay, 1 unit area. I'm not worried about that. Think. Okay. think. Okay, see, do you agree that I want to move this topmost layer, I have to apply force or not? I want the top
Yes,
layer
sir.
to move. I want the top layer to, right now they're not moving, right? Liquids may be at rest also, no? So they may not be moving. So I have to apply force to which layer? The topmost layer. Okay, I want the topmost layer to move with a speed of 1 centimeter per second. I'm just making it 1 unit right now. 1 unit, doesn't matter. Okay, but right now the velocity is how much? 1 centimeter. Agreed with this? I think this part is clear. I want it to move with how much speed? 1 centimeter per second. This layer is at a height of, okay, not height, okay, but at a distance of 1 centimeter from the bottommost layer, and definitely I need to apply what? Force. Think and tell me. Okay, do you agree that I must apply a force which is equal to exactly the opposing force between these layers or not? I should oppose this force or not? Think.
Yes, sir.
If I tell you the opposing force is 10 newtons and the force I apply, Mike, force apply is only 2 newtons. Now you think, will this happen or not happen?
It won't happen, sir.
It won't happen. Why? Because how much is the opposing force?
10 newtons.
10 newtons, and you are applying how much force?
2 newtons.
That means this is not going to happen. No chance. Okay. But if I come back again, okay, on top, okay, and I apply a force which is equal to 10 newtons, now this will happen or not? What do you think? Yes, because
So like it will move but in zero acceleration.
that's why the velocity will be at 1 centimeter per second.
Yes, sir.
Okay. But did you understand, guys, what I'm saying? Is it making sense today what I'm speaking? Okay, let's go to, this is for water, let's go to honey. Now it will make sense. Look at this. Let's go to honey, okay? Same picture, everything same. I want this topmost layer in honey to move with 1 centimeter per second. Think and tell me, will there be an opposing force or not?
Yes, sir.
Okay.
Yes, sir.
Will it be 10 or more than
Yes,
10?
sir.
Just tell me that. More than 10?
10.
More than 10.
So
Very
more than
good.
10.
Very good. More than 10. This opposing force in honey will be how much? Let me tell you exactly. 200. That is 200. 10, no? So 10 times of 200 is how much? 2000. Just imagine. This opposing force in honey will be how much?
2000 Newton.
So,
2000 newton.
yeah. So the bottommost layer is moving with 0 meters, centimeters per second. But I want the topmost layer of honey to move with how much? 1 centimeter per second, just like the previous case. Okay. Yes. In previous case I needed only how much? 10 newtons, but this time I need okay. Now think and tell me, how much opposing force should I apply? Same or much more now? I want to get rid of this opposing force, otherwise this liquid will not move with so much speed, and for that I have to apply an opposing force of how much?
2000 Newton.
At least 2000.
The more the force that you need to apply to maintain this gradient, the velocity change, okay, the more the force you need to apply. It means it is a liquid or it's a viscous liquid?
Viscous liquid.
It's a not viscous, okay, it is a viscous liquid. Can you understand? Did you understand this example, guys? You really understood?
Yes, sir.
Should I give another try? I don't know whether I'm speaking sense or not. 2 layers. Did it make sense? No. Bottommost layer, topmost layer. Okay, let's say topmost right now, doesn't matter. I want the top layer to move forward. I want it to move with only 1 centimeter per second. The area I have taken is how much? 1 centimeter square. Let's do in CGS system right now. Okay, the area of the liquids. And you know what? Right now the liquid is not moving, but I want the liquid topmost layer to move with how much? 1 centimeter per second in the forward direction. Do you agree that I need to apply force on these layers or not?
Yes,
Yes,
sir.
you said yes. Okay, this is water, by the way, water. Let me tell you exactly how much force you have to apply. Okay, you have to apply a force of 1 dynes. How much dynes? For this to happen, don't forget this. Okay, yeah, for this to happen. But when I take the same case, and by the way, what will this 1 dynes do, guys? It will help us to get rid of what?
Opposing force.
Opposing
Viscous
force. Viscous force. And the viscous force is also how much?
So 1 time.
But this time I'm going to write minus 1 dyne because it's the opposite direction, no? Okay, I think you got my point.
Yes, sir.
Okay, this is water. Now I go back to what? I go back to honey. Now tell me, can I make just imagine this is honey now. Can I make the topmost layer move at 1 centimeter per second in honey also? Yes or no?
No,
Yes.
sir, the force should be more, right?
The force should be high or very high?
Very, very high.
The velocity gradient is same. The velocity gradient is same. The area is same. Okay. Here also the velocity is gradient how much? 1 centimeter per second per 1 centimeter. That's the velocity gradient. Here also the velocity gradient is 1 centimeter per second per 1 centimeter. Okay. Here also area is 1 centimeter square. Okay. But this time the force that I will need to really make this topmost layer move at 1 centimeter per second will be very large compared to what? Compared to water. That means the opposing force is large here or very, very large here.
Very, very large.
And you know how much is that? I told you 2000 dynes. 200 times, not 2000, sorry, this time it will be 200 times. Okay. So now you think and tell me, does it make sense now what I'm saying?
Yes, sir.
Okay, I cannot apply 1 dynes here this time. If I want this topmost layer to move with 1 centimeter just like the water, I have to apply 200 times stronger force in honey compared to water. I think now it's making sense. Are you clear?
Yes, sir.
And that's why I'm going to conclude now. Okay, that's why you know what I said, the more the force you apply, you need to apply, okay, to make the liquid layers move with so much conditions, with these conditions. Okay, that number is known as coefficient of viscosity, which is 1 in case of water. Coefficient of viscosity is 1. Okay, I remember, right? You remember, right? And coefficient of viscosity in what? Honey is how much? 200. 200. What does it means indirectly? Indirectly it means what? If I need some force to make water move, okay, under same conditions, if I want the honey also to move, then in case of honey I will need force, or I'll need 200 times stronger force
200 times stronger.
than the water, and that means the coefficient of viscosity is 200 times, or for honey is 200 times that of value of what? Water. So what is coefficient of viscosity? Please tell me, guys. Is coefficient of viscosity the velocity gradient? No. Is coefficient of viscosity the area? No. What is coefficient of viscosity, guys? It is the force. Look at this. What is coefficient of viscosity, guys? It is the force required to maintain how much velocity gradient?
1 centimeter per second.
1 unit. Just call it 1 unit. Just call it 1 unit. 1 unit. Okay. So what is the coefficient of viscosity? Is it the force required to maintain how much velocity gradient? 1 unit.
1 unit.
For any two liquid layers which have how much area? Unit area. Under same conditions, see, we're comparing these two liquids, and we are very nicely can realize, okay, under same condition which liquid we have to apply more force. Okay, I'm done with this, but this is the next problem. It's a very nice problem. I'll help you out with this. Maybe you will understand. Okay, this question I'll just take a picture, then I'll do it. Then I have one more topic. I'll do it very fast. Very boring day I'm feeling today. You guys know also, no? I think no.
Yes, sir.
Yes, even I'm feeling very bored. Okay, but at least let me do this. Let me just do this one, huh? See this one. You will understand this. It's a very nice problem. This till here we can do. No. Till here we can do. That's it. No need the other part. Okay, see. So what is this question? Okay, a circular metal plate. Think about this, huh? Check. This is the liquid we have, which is trying to flow to the right again. I'll tell you what is this. Okay, it's a castor oil. Okay, they've written it. Castor oil, no? Yeah. Castor oil. Check this one. Castor oil, 2 millimeters written. 2 millimeters thick. That means from here to here, the thickness of the castor oil is how much, guys? 2 millimeter. Can you understand this topic till now? Just check, guys. This castor oil is going to flow. That's what we are going to talk about. Okay. And you know what? The question says a circular metal plate of radius 5 centimeter. Let me draw that also. Say this one. Circular metal plate of how many centimeter? 5 centimeter. Question says rests. Right now it's at rest. Okay. Rest on that surface, on the layer of castor oil. This one. Are you clear with this? What is this, guys? This is circular metal plate. I think you are fine till now. Okay. Now the question also says the coefficient of viscosity. Let me just mark that part. The coefficient of viscosity is this much for this castor oil, of course. Okay, so coefficient of viscosity is given. Let me just write down there also. 15.5 dynes centimeter minus 2 and seconds. Okay, this is what we got. Okay, calculate the horizontal force required to move the plate with a speed of 5 centimeter per second. Do you understand that this metal plate has to move on top of this, okay, with a speed of how much? 5 centimeter per second. Okay, so now all of you think and tell me. Okay, if I want the metal plate, okay, the metal plate, which is this one, to move with 5 centimeter per second, the radius is given, I think, yeah, that is 5 centimeters radius. So if I want this metal plate to move with 5 centimeter per second, what should happen to the topmost layer of the liquid, guys?
It should move with 5 centimeters.
Very good. Yes, now Sangam's brain is working. Okay, if the metal plate has to move with what speed, guys? 5 centimeter per second. Don't worry, you guys got it. Okay, you will get it, I'm sure. I'm 100% sure that metal plate should move with 5 meters per second, and the metal plate is on top of what oil? Which oil? Castor oil. Okay, I don't know what is that, I've not seen. Okay, castor, not even okay, castor, no. So what should be the speed of this topmost layer, guys?
5 centimeter per
5
second.
centimeter per second. Is this point clear with all of you guys? All of you? Only this point. Other things, don't worry about this right now. Is it okay for all of you? Abhijit,
sir.
Paul, did you understand?
Yes, sir.
Yes, sir.
Okay, Abhijit, Vinayak, did you understand? Is there? Vinayak is there?
Yes, sir.
Okay.
Yes, sir.
Okay. Now check. Yes, now you think and tell me. Okay, now check. See. Now you check and tell me. The question is, how much should we apply force or not for this to happen? We should apply force, right? Because it was at rest, no? So how much force should be applied? What do you think? We should apply some force or not? How much force should we apply for this to happen? Because it was rest, I want it to move with 5 centimeter per second. Do you agree that we should apply a force that will at least overcome the viscous force or not?
Yes, sir.
Yes, sir.
Okay, so we should apply force that should overcome which force?
The viscous
The viscous force. Do you agree that we have to find the viscous force only? That means, right? And what is the formula? The formula is this one. Okay, where you know what they have given? They have given eta, right? They have given eta. More eta, I have to apply more force to overcome the viscous force. More area, I have to do that. Velocity gradient is easy to calculate because the difference between this and this is how much? The bottom and the topmost layer.
2 millimeter.
2 millimeter.
No, the difference in velocity, dv. 5 centimeter per second minus 0 centimeter per second. What is the dx between these two layers? 2 millimeter. So I think you can find dv by dx, right? Check. Yeah. So can you find dv by dx or not? Check, guys.
Yes, sir.
Because the speed of this is 0, so speed of this is this 1/5. So I just have to subtract these two. I'll get the change in velocity for this much distance, which is 2 millimeters. So I'm just going to divide this by this. Okay.
So why will it be 0 centimeter?
This is the bottommost layer, right? Check.
Oh, yes, sir.
Yes. Okay, the difference, no, like that. Okay. So yeah, so velocity gradient we got. Okay, we got the area. So I think you can understand. We only need to calculate what, guys? Viscous force only. Okay, I'll do like this. Okay, I'll stop for today, guys. Only this much. Next day when I meet, okay, I'm not so sure, okay, whether I can take Thursday or not, because I told you, no, I may go to Assam. Okay, so I'll come back and we will meet again. Okay, I will inform you and all. Okay, in between I will make sure today I'll send you the notes for viscosity also. Okay, today I want to stop. Okay, guys, I have to attend some calls here.
Okay, sir.